Hello, everyone. Welcome back. Today, we're going to talk about polynomials. We're going to introduce what are polynomials, and then in the future, we're going to talk about adding, subtracting, and multiplying polynomials as well. So, polynomials and related equations have applications in many areas such as science and economics. But what is a polynomial? A polynomial basically has a variable and it has a constant term, or at least some of the above. So a polynomial can be described this way. Y oh, y equals axn plus bxn minus 1 plus cxn minus 2, etc., all the way till we get to, um, doesn't matter, some other variable. Let's just say a naught x squared plus b naught x plus c naught, for example. So basically, a polynomial, what defines something as a polynomial is, do we just have variables, coefficients, and constants? Now let's talk about what those mean exactly. So a variable is a letter or symbol with exponents used to represent an unknown number. So for example, x and y and theta are variables because they're representing something that we don't know. A term is a product of numbers and or variables. So it's basically a coefficient and a variable. Now that variable can have an exponent. A term is also something like -4, which is just a constant, because -4 technically is the same as -4 multiplied by x to the power of 0, right? And so this also counts as a term. Now there's two parts of a term. There's the coefficient, which is the number attached to the term that we're multiplying the variable by, and there's the variable part of it, which includes something like x or y or theta or anything else like that, and it can also have a power to it potentially. Now, a constant term is a term with no variable, so just a number. So in this example here, we have 2x squared minus 8x plus 4. Plus 4, this is just a constant term because there's no variable attached to it. Now, what about like terms? Like terms are terms with the same variables. So, for example, 2x and 4x are like terms because their variable is x. And because they're like terms, we can actually add them together. We could add them and we could say, if we add 2x, I guess it says -4x, actually, not 4x. If we add them together, we'll get -2x. We can add them together because they have the same variables. Same with 2x squared y and 18x squared y. The variables are the same, so we could add these, we could subtract these, we can collect these together and make them into a simpler term. Here are some examples of things that aren't like terms. For example, 3x and 3y are not like terms because one is 3 multiplied by x and one is 3 multiplied by y. And assuming x does not equal y, these would not be like terms. Similarly, here we have -4xy squared and 3xy. Well, here in the first term, we have xy squared for variables. In the second term, it's just xy. There's no squared on the y, and so those are not the same thing, therefore. So that's what we mean when we say like terms. You'll often hear the phrase collect like terms, and that basically just means to add and subtract them depending on what the equation is wanting in order to make something simpler, right? Rather than having 2x squared plus 5x squared plus 6x squared, if we just add those all together into 13x squared, that is much more simple than having three different things that are the same that we're adding together. And also constants are also like terms, right? So 10 and 4 and -8 and plus 12 or 5, all of those are like terms, right? Because we can just take any constants and add or subtract them together and get just one final constant. Okay, so a polynomial is a collection of any terms separated by a plus or a minus sign. Keep in mind, though, the variables must have positive exponents or a zero exponent in the case of the constant term, and variables cannot be in the denominator. Now, I want to point something out here, though. When we have a constant, we can still have something in the denominator with that, or we could have 3 over 2x squared, for example. So we can still have a denominator in terms of our coefficients or our constants. We just can't have variables in the denominator. So, for example, 3 over x would not be a polynomial, nor would it be able to be a part of a polynomial. So let's start with types of polynomials. So we have monomials, which are polynomials with one term, like set x, right? This term has two parts to it. It has a coefficient and a variable, but this is still just one term, 7x. There's no plus or minus or anything. The second one is a binomial. It has two terms. Here we have 5y is a term with a coefficient and a variable. And then we have plus 2n. So these are two terms, two terms, whereas this one is just one term. A trinomial, sorry, a trinomial is a polynomial with three terms. So for example, 10x plus 1d minus 4y, that's three terms. Let's talk about the substitution of polynomials. We might be asked to figure out or evaluate a polynomial at a certain value, right? Because the thing is, polynomials, they have some unknowns, but if we're given a certain value to place in those unknowns, we can find an answer. So here's a few examples where they put in a value and evaluate it. So here what they did is they said our polynomial is x squared plus 2x plus 1, and they said, okay, let's plug in 4 for x. So that's what they did in the first step. They just put 4 in place of x. Then in the second step, they used their order of operations, which we talked about in the last unit. They used their order of operations to then say, well, exponents are next. So they squared the 4 and put it as 16. Then in the next step, they evaluated the multiplication. So they said 2 times 4 is 8, and they got 8 here. And then they added 16, 8, and 1 in the last step to get the answer is 25. And it's a similar method for these two examples, right? Where we have, in this one, we have the same polynomial. We're just evaluating it at a different point where x equals -2. And here we have a different polynomial, and we're evaluating it at a different point. But the key is for these is whatever number we're evaluating it at, that's what we need to sub into the respective variable. But if we have unknowns, we're not able to do it. We're not able to evaluate something unless the question tells us what those unknowns are. All right. Well, there's polynomials. Let's answer some questions about polynomials. This one first says, which expressions are polynomials and give reasons. So A would be yes, and I'm not going to write down the reason, but I will say the reason because I think it's important. So A is a yes, and why is A a yes? It's because it does fit the definition of a polynomial. It is a collection of two terms, right? So that would be a binomial, which is type of polynomial, we said. And there there are no symbols that are not allowed for a polynomial here, right? It's just 5x, which consists of a coefficient and a variable, which is okay, and then -3, which is a constant, and all of those are okay. So that's all good. Now B is also yes, this would be a polynomial for the same reason. The only difference here is we have something with squared, but we are allowed to have exponents as long as they're positive exponents in our polynomial. So this is still allowed. This one, C, would also be a polynomial for the same reason, right? We have 2 times a variable, right? So we have coefficient variable. Then for 3y, same thing. We have coefficient variable. And then we have a subtraction sign and x squared. So that all looks good. Now what about D? Is D a polynomial? No, it is not. The 2 is okay, right? This constant term is okay, but then we have plus 1 over x. Now, 1 over x is the same as x to the power of negative 1, which is a negative exponent, so it isn't allowed, right? Or likewise, something we mentioned earlier is for polynomials, we're not allowed to have exponents, or not exponents, we're not allowed to have variables in the denominator. And in this case, we do, right? We have an x in this denominator, and we can't have that. We can only have variables in the numerators. And so that's why it's a no. Now, what about 3? This is just a constant term. And I would say, yes, this is okay. This is a polynomial, even though it doesn't have any variables, because constant terms are included in polynomials. So it's okay. What about F? F is a no for similar reasons to why D was also a no. And that's because we have a variable, which is y, in our denominator, right? We have y squared in the denominator, which does count as having a variable in the denominator, and so that's a no-go. Okay. In each expression, is each expression a monomial, binomial, or trinomial, and give reasons? Well, let's remind ourselves what each one of those things means. Well, a monomial means we have just one term, right? So either that term is a constant term, or that one term is a coefficient and a variable. So let's pick out all the monomials. Well, this first one, B, would be a monomial, right? Because we just have our coefficient, which is -1, and then we have our variable of x squared, so that's a monomial. Same with 4x, our coefficient is 4, and our variable is x, so that's good. This one here, D, is also a monomial because it just has one term, and in this case it's just a constant term of 10. So no variable, just a number, so just a constant term. What about binomials? This is where we have two terms. So for A, this would be a binomial because there's two terms, right? The two terms are 3x, which it consists of the coefficient and a variable, and then 4, right? Which 4 is a constant, so that's two terms. Same with C for similar reasons, right? We have our constant, which is -2, and then we have our negative y squared, right? Which is our variable term with -1 is the coefficient and y squared as our variable. All right, and then H also would be a binomial because we have two terms. We have -3, which is a constant term, and then we have -y, which consists of our coefficient of -1 and our variable y. Good. Now the rest are trinomials, E and G. Now why are they trinomials? Because it did say give reasons. Well, there's three terms, right? We have 5, 2x, and -2x, and 3y. So that's three terms, right? Same with here, 5x squared, 4y squared, and x. Well, again, that's three terms, right? And so there we go. All right, so this one says to state the coefficient in each term. So let's remind ourselves, what is a coefficient? A coefficient is the number, basically, that is beside our variable. Or, or the question we could ask ourselves to know what's the coefficient is, what is the variable? Or sorry, what is the variable, and what are we multiplying that variable by? Because whatever we're multiplying the variable by, that is the answer. Good. Okay. So here we're multiplying x by 14, so 14 is our coefficient. Here it's 7. For a, it's actually 1, right? 1a is the same as a, so there's actually an invisible coefficient of 1 here, so I'll say 1. For d, the answer would be -1, right? Negative b squared is the same as -1 times b squared. Here we have pi r squared, so keep in mind pi is actually a number, not a variable. Pi equates to approximately 3.14159 and so on. And so pi would be our coefficient here. And then over here, root 3 is our coefficient, right? Because everything else is just variables and exponents. So there we go. Number 7 says, state the constant term in each polynomial. So the constant term is the term that does not have any variables attached. So a constant term is just a number. So in this first example, A, the answer would be 6 because 6 does not have any variable attached, it's just on its own. For B, it would be -5 because -5 doesn't have any variable attached, it's on its own. For C, the answer is 7, right? 7 doesn't have a variable attached, whereas -3x and -3y, those do have those variables attached. D would be -2/5. E would be that there is none, or you could argue that 0 is the constant term, because if we added 0 or subtracted 0, we'd have the same thing. So in this one, you could either argue the constant term is 0, or that there is no constant term, because both 7 and -5 are attached to variables. They're coefficients, not constants. And then x over 2, well, there are, same kind of thing. We could argue that there are none, or that the constant term is 0, because the over 2, well, that's part of the x, right? That's the same as 1/2 times x, so that would be a coefficient and not a constant term. Good. All right. This next one says the opposite. It says state the coefficients in each polynomial. So a coefficient is these are the numbers that are multiplied by variables, right? So there could be multiple, right? If there's multiple variables, there could be multiple coefficients here. So for example, A, it would be 6 and 2. So everything except the constant, right? 3 is a constant, not a coefficient. And 6 and 2 are the coefficients, right? Because they're multiplied by P, and 2 is multiplied by Q. Similarly for B, I would say it's 1, -2, and 9 are the coefficients, right? Because again, for A is the same as 1A, right? And then for B, we have -2 attached to it. And then for C, we have 9. All right, what about for C? C is 1.8, right? Because 1.8 is part of the same term as C, and 32 is the constant, so that would be a no. How about for D? We have 2 pi r, so 2 pi would be the coefficient. And then for E, let's see, it would be 7 and -3, but not 9, because 9 is a constant. And for F, we would have 4.9, -1.2, and -0.5 as the three coefficients, but not 2, because 2 is a constant. Okay, awesome. The next one says, state the like terms in each group. Now let's review. What is a like term? Well, like terms are terms that have the same variable to them. And I want to also make it clear that like terms must also have the same exponent to them. So for example, a and a squared are not like terms because we couldn't add those together and get something simpler, right? Like terms are things we can collect and make into one term if we wanted to. So it says to state the like terms in each group. I'm actually going to highlight them instead of stating them. Let's grab, I want a purple highlighter. That would be good. Okay. So let's look through. We have 5a, 3b, 5c, a squared, -a, 3d, and 3e. Well, let's cross out what is out here. So first off, we know that b and c are not the same, and d and e, so it has to be something to do with these a's, right? However, what's different about these a's? Well, this one's a squared, so that's a different exponent, whereas these two would be left, and these two are the like terms, right? Because basically everything else other than those two, other than these, everything else that is there either has a different variable, so c, d, b, or e, or it has a different exponent. And so that's what makes everything else not like terms to one another. It's only 5a and -a that are like terms. And we could add those together and get 4a, right? So we could collect those like terms. Good. All right. Let's do the next one. B, we have 4x, 3y squared, 4z, 2y, y squared, and 4w. Well, I would say 3y squared and y squared are like terms because we could add them up and we could get 4y squared. So that's good, right? They don't have the same coefficient, but that's okay. They don't have to have the same coefficient. They just have to have the same variable and the same power to be considered like terms. Okay, what about C? C says 9g, 6h, 9g squared, 1/9 g, 1/6h squared, and g squared. Okay, this one's interesting. There's actually two sets of like terms. So 1/9 g and 9g are like terms to one another. And there's actually another separate set of like terms because g squared and 9g squared are also like terms to one another. So I'm not sure if that was by mistake. I want to make it clear it's not that all four of these are like terms. It's that there's two pairs of like terms, that 9g is a like term to 1/9 g because they both have that same variable and the same degree, and then like with the same power. And then 9g squared and 1g squared also are like terms as well. So there's two sets of like terms here. Whereas in the other ones, I don't think there was a second set of like terms. Good. All right, and for the last one, it says 16d, d squared, f, -8, 0.5d, and 7d cubed. Okay, actually, I don't think it was by mistake because there's also two sets here as well. There's 16 and -8, right? Those are both constants, and constants are like terms, right? We could add 16 and -8 together and we could get 8, right? But also, there's another set here of d and 0.5d, right? Those could be added together to get 1.5d, right? They have the same, not coefficient, they have the same variable and the same power, and so they would work. Very good. All right, so let's not bother with 20 and 21 for today. Those will be questions for another day. But let's do 10 and 11 before we finish off today. Okay. So the next one says evaluate 3n plus 4 for each value of n. So if n is equal to 1, we would have 3 times 1 plus 4, which is 3 plus 4, which is 7. If n is 3, we would have 3 times 3 plus 4, which is 9 plus 4, which is 13. For 4, we would have 3 times 4 plus 4, which is 12 plus 4, which is 16. For this one, we would have 3 times -1 plus 4, which is -3 plus 4, which is 1. So there we go. Now they're asking us to evaluate 3x minus 5 for each value of x. So the first one is 0, so 3 times 0 minus 5 is equal to -5. Then we have 3 times 1 minus 5, which is equal to 3 minus 5, or -2. Then we have 3 times -1 minus 5, which is -8. Then we have 3 times 7 minus 5, which is 21 minus 5, which is 16. And there we go. Awesome. Okay. Well, that's very good. Okay, well, that will be everything for today. Next time, we're going to be talking more about adding polynomials together with each other, collecting those like terms. And then in a future day, we'll also do multiplying and dividing polynomials in the future as well. So stay tuned for more polynomials. There will be a lot more about polynomials than what we learned today. But I feel that today gave us a good introduction, right? We learned about the constants, coefficients, and the terms and variables, everything like that. We discussed what are like terms, and we really got those definitions very solid, I feel. So that's the important thing. That's the important place to start, and we'll continue with that next day. Good work today, everyone, and goodbye.